To understand the constraints or potential weaknesses of hash functions, there are two concepts we need to discuss. The first is the pigeonhole principle, and the second is the birthday paradox. First, let's take a look at the pigeonhole principle. Imagine we have 9 pigeonholes. If we have 9 pigeons, then 1 pigeon can be placed in each hole. That is, suppose we have n number of pigeons and m number of holes. If n equal to m, that means there's exactly 1 pigeon per hole. Now, if we add another pigeon, then there will be 1 hole with 2 pigeons. That is, if n, the number of pigeons, is greater than m, the number of holes, then there's at least 1 hole that must have more than 1 pigeon. Now let's apply the pigeonhole principle to another problem. How many people do we need to have in a room such that there's a good chance that 2 of them will have the same birthday? There are 365 birthdays, and we can think of these birthdays as the pigeonholes. How do we calculate the probability that 2 people in the room have the same birthday? Obviously, if we want the probability to be 100%, we need 366 people, and that's the pigeonhole principle, because we have 365 birthdays, or 365 pigeonholes. So we need 366 pigeons, or people, in order to make sure that 2 of them will have the same birthday. Now suppose we only need a good chance, say only 50% chance, that 2 people in a room would have the same birthday. How do we calculate how many people do we need in a room? We can solve this problem using the following procedure. We can model this problem of having n people choosing from k days as their birthdays. Of course, k is 365. If we allow everybody to choose any of the k days, then there are k to the n that many scenarios, because for each of the n people, they can choose any of the k days. So there are k to the n that many possible scenarios. On the other hand, if we insist that no 2 people should have the same birthday, then the number of scenarios is choosing n out of k without replacement, and that is k times k minus 1 times k minus 2, so on and so forth, and times k minus n plus 1. Because for the first person, he can choose any of the k days. And once he makes his choice, then the next person can only have k minus 1 choices, because we don't want this second person to have the same birthday as the first person. And once the first 2 people have chosen their birthdays, then the third person can only have k minus 2 choices, and so on and so forth. So this is the number of possible scenarios when we insist that no 2 people should have the same birthday. Then we can use this formula to compute the probability that there's a scenario where 2 people share the same birthday. And this can be approximated to n times n minus 1 divided by 2k. Therefore, if we want this probability to be 0.5, meaning that there's 50% chance that 2 people will share the same birthday, then n should be the square root of k. Again, this is just an approximation. If k is 365, then the square root of k is 19. That means, as an approximation, if we have 19 people in a room, there's a good chance that 2 of them share the same birthday. I have tried this in my class every year with the students in my classroom, and it always works out as the math tells us. Once we understand the pigeonhole principle and the birthday paradox, we may realize that some of the properties of hash function seem to contradict each other. In particular, a hash function can take as input data of any size, and the output is always a fixed size. Since the size of hash value is fixed, that means that there are a fixed number of possible hash values. On the other hand, since the input to hash functions can be of any size, that would mean that there are many more possible inputs to the number of possible outputs. In other words, there are many more pigeons than the pigeonholes. Then, applying the pigeonhole principle, many inputs will map to the same output hash value. In other words, many different input messages will have the same hash value. But this violates the property of collision resistant. However, if we take a closer look at the hash function properties, in particular the collision resistant properties, they only say that it should be computationally infeasible to find 2 different messages that have the same hash value. It did not say that it should be mathematically impossible. to find such collision. In other words, although it is mathematically possible to find a collision, the hash function property says that we want to make it infeasible or impractical to find such collision. So how do we accomplish this? Obviously, the larger the number of possible output hash values, the harder it is to find a collision. In other words, the longer the length of the output hash value, the better. In short, to avoid collision, we should use longer hash values.